the one which is moving over here in the Earth's above the space over here, which is not blinking, as well as it's going to have a continuous movement over there, right? So it is actually the Earth's space station what we have. It's like a very big satellite which is revolving around the Earth. We do have satellites which are called as natural satellites like moon, but we do remember about the satellites, those artificial satellites only, which has been sent by the man most of the time to observe what happens around the Earth with the help of so many scientific devices. Few of them includes camera. So where we'll be having the images of the Earth, the fifth satellite which has been sent as the Sputnik, and moreover we do have 20,000 satellites which is revolving around the Earth as of now, and these are few of the images which has been taken by the satellites, which says us about the glaciers which is melting or what weather we do have over there in the poles. And when we are looking at the weather report, that has also been given by the satellites only. The satellites are not only useful for weather reporting and other stuffs, but we are also using them. Where we are exactly, that can be given with the help of a satellite mapping what we have. At the same time, we do have mobile phones as well as the televisions, which works based on the satellite as well. So about those satellites, whatever the information we are getting, one of the biggest one is, as I told you, it's going to be the space station, where peoples are working in turns. 6 months once 6 peoples will be going over there, and they'll be working over there with the scientific experiments. About those space as well as the satellites only we are going to do with today's session. The small dot what you see is actually the space station. Let us look into the Kepler's law with today's session. So there are 3 laws of Kepler's. Before Kepler law, there are 2 persons who said about how the planets are revolving around the Earth. That is how the gravity makes this as possible. So the first person who said about this is nothing but Ptolemy. What was his conclusion is nothing but he said that Earth is the center of the universe. All the planets and other stars and other stuffs are revolving around the Earth by having the Earth as the center of the universe. This is a concept which has been said by the Ptolemy, and he said that all of them are revolving around the Earth in circular orbits. This was being believed, and it was called as the geocentric theory until the Copernicus have given his thought about the same planets. What he said is nothing but Earth is not the center of the solar system or the universe. Sun is the center of the solar system, which is called as heliocentric theory. In this also he said that the other planets are revolving around the sun in the circular orbits by having the sun at the center of it. Then after them only, the third person, who's Johannes Kepler, have given the 3 laws of orbital motion, which are like the law of orbits, the law of areas, and the law of periods, or the 3 laws which has been proposed by Kepler. So when it comes for the law of orbits, the law of areas, and law of periods, they do have a different name as well. Let us look into the law of orbits first. The law of orbits says that all the planets revolve in elliptical orbits with sun at one of the foci of the eclipse. So he said all the planets are revolving around the sun in an elliptical orbit, not in the circular orbit. Let us prove it with the help of a small experiment over here. When I'm going to look at that over here, I have taken a cardboard where I'm going to fix a white chart with the help of the pins, and I'm going to take 2 points over here on this. On that I'm going to fix 2 pins. F1, F2 are the point what I'm considering, and these 2 points are going to be connected with each other with the help of a extensible string, that is which can be extendable, and with the ring I have connected it over there. Then I'm fixing the 2 pins position over there as F1 and F2 over here. Now I'm going to take a pencil. The pencil is going to be connected, or it's going to be inserted with the circle over there, and by holding it we could able to extend it towards the upward like this, so that the points are fixed. And I'm going to draw a circle around it. If you're going to look at it, the circle is nothing but a ellipse what you're seeing over here, where F1 and F2 are the 2 points which is being taken as the foci of this ellipse, and sun is going to be appear on any one of this foci. and the planets are revolving around the sun in this elliptical orbit only. Where we are taking this on over here, A and B is going to be the extreme edges of this. When I'm trying to find out a position P, the distance of F1P and F2P, if I'm going to add, the addition of that will always remain a constant, as we have done in the previous one. So that's the same thing in a solar system. In a planetary motion is also been given. Whenever you're going to have a planet at a position P, F1P and F2P is going to be always constant, which means that the sun is going to be placed in any one of the foci of the ellipse what we are going to have over here. Kepler's second law, or we used to call that as law of orbits. The area swiped by the planet in the given time will always remain constant. There is a line joining the sun and planet sweeps equal areas in equal interval of time is the second law. Let us consider any two of the points or any two of the positions. Let me take the first one as P1 and the second one as P2, and the area covered by the planet within 30 days is going to be taken as A1. Similar way, I'm going to take two more points which is named as P3 and P4, and the area covered by that within 30 days we are going to consider that as A2. So the law of area says us that in the equal period of time, what is the area spied by the planet will remain same, that is A1 is equal to A2. This is happening because far away from the sun the planets will be moving slower, closer to the sun it will be moving closer. So based on that only the third law has been given, which is law of periods. The square of the period is going to be directly proportional to the radius of the major axis what we are going to have, which is the cube of it. This is what is the third law is telling us about. So whenever we are going to look at the next one, based on this, how much amount of potential energy the planet is going to hold or must be having to reach that particular orbit is the next step what we are going to do over here. So whenever we are talking about the potential energy or gravitational potential energy, generally it will be given by mass times the gravitational potential times what is the distance at which it's going to be placed. As we know, the planet, that is from the center of the earth, when the object is going to move away from the surface or moving towards the surface, the force will get reduced. So the force and the distance are going to be inversely proportional to each other. This inversely proportional should be represented in the equation. So that to represent that only we have a minus sign over here. When we are having this minus sign, F is equal to minus gmem over r square. G is the gravitational constant, m is the mass of the earth, m is the mass of the object which is going to be on the earth's surface, and r is going to be the distance of that from the surface to the earth. As on the earth's surface the amount of force will be very high, and the force what we feel is also called as the weight of the object. So over short distances compared to the earth radius, the gravitational field spreads out very little. That applies to distance of few hundred kilometers. Over these distances we can calculate the energy to lift a mass simply by, which is nothing but potential energy, mgh, which is mass times gravitational field strength times the height of the object. So when I'm trying to write it, the weight of the object should be equal to the gravitational force over here. So mg is equal to minus gmem over r squared, where m and m are the mass of the object which get cancelled and gives the gravitational strength as g is equal to minus gme over r squared. So as the height increases, the force gradually decreases, as being represented by the negative sign over here. So when we are trying to look into the next thing over here, what is the next step we are going to have is nothing but the continuation of the derivation of it. Let us consider the rocket which is going to move away from the surface of the earth. The distance which is being traveled by the rocket is going to be very high compared to an object away from the earth's surface. Actually the rocket is going to have three stages of splitting. After that only it will be reaching its orbit. So the first stage is going to be equal to the radius of the earth. As you're seeing over here, the radius of the earth, if you are taking that is small r, the first stage when it's going to reach, the distance from the center of the earth to the satellite is going to be 2r. when you are going to take the 2r the whole square as the denominator, the force is going to get reduced by 4 times over here. When we are trying to go for the next stage over here, then we are going to have that as r plus r plus r, which is going to be 3r the whole square, so that we are going to have that as 9r squared over here. That means that the force is going to get reduced by 9 times over here. When we are coming for the fourth stage, that is third stage over here, 4 times of the radius of the earth we are going to have, so it's going to be 4r square what we are going to have, which is the force reduces by the 16 times. So when this distance is going to increase in a huge amount, automatically the amount of force associated with that get reduces. That means that the racket is moving away from the earth gravitational force of attraction. So the work done is equal to the potential energy, but we have to take the changing force into account. To calculate the work done, we have to integrate what is the expression what we have over here in the above. When we are integrating with respect to r and 3r, we are getting the actual equation over here. By integrating the r square, we will be getting that as r over here. When we are substituting the limits over here, we are going to have that as 2m GMEM divided by 3r. So as a result of it, what is the conclusion we are getting is nothing but GMEM over r. What are we going to have here is the formula for the gravitational potential what we are having actually here, right? So the GME over r is going to give us about the gravitational potential what are we actually going to have. Otherwise we can write that as what is the distance moved by the mass times the gravitational potential at first height minus gravitational potential at the final height. Over here first height is r, final height is 3r, that is why the derivation is 2gme over r. So this is a formula for the gravitational potential. Let us look into how the satellites are revolving around the earth. Whatever the communication, maximum of the communication happening now is based on the satellite only. There are two types of projection of the satellites above the earth's surface. One is going to be the geostationary satellite, the other one is going to be the polar satellite. So when we are talking about the geostationary satellite, we are going to have the satellite which is projected above the earth's surface, which is going to be 36,500 kilometers away, which is having the time of 24 hours to revolve around the earth. Let us look into how satellites are actually working. We do have receiver stations as well as we do have a transmitter station when it comes for the satellite communication. So from a particular station, the rockets will be receiving the transmitting signals and they will be processed, and which is going to be received by the receiver ends, which is also called as the downlink on the earth's surface. So with the help of this, the communication of them is going to be very easy for us to do. When we are looking at the geostationary satellites, what we are going to have over here, geo means earth, stationary means it's going to remain same or it's going to remain constant. So the geostationary satellites are the one which appears to be in the same position when we are going to look from the earth's surface. What are we going to have, right? So the geostationary orbits should have the same time as the revolution of the earth, then only it will be appears to be the same, and it will be helpful for us in observing the information about the earth's surface. What are we going to have over here, right? So when we are talking about the geostationary satellites, we will be able to find out that it's having 24 hours of revolution and 35,900 kilometer orbit distance. It is also called as the Clark orbit. The reason for that is the person who found who coined this term first is about the Clark. To honor him only, we used to call that orbit about the 36,600 kilometer orbit as the Clark's orbit. The next one, which is called as the polar orbit or polar satellites, we used to call them out. They are going to be placed above the earth's surface by 1000 kilometer. When you are having 3 satellites which is placed at the vertices of the isosceles triangle, they will be able to get all the information about the earth. The solar satellites are the one which is above 1000 kilometer and which is revolving around the poles what we have over here, they will be able to complete one revolution within 12 hours. So as they are revolving around the poles, we used to call them as polar satellites, and the geostationary satellites are called so because they are going to be appearing at the same as from the Earth's surface. So these are the two which we need to know.